In last video, we talked about the QDA under the multivariate normal distribution setting. So in this video, I'm talking about linear discriminant analysis under the general multivariate normal distribution settings. So assumptions. Well, the assumption is that here I want to highlight a little bit. We have one variance covariance matrix for all classes. Okay, so and the assumptions for the QDA. Assumption for the QDA is that each class could have different variance covariance matrix. For example, the correlation between x1 and x2 under this normal distribution is positive associated, right? And the variance covariance matrix for this one distribution is negative. So there is the sigma c, there is sigma d, and sigma c and sigma d are different. But in the linear discriminant analysis, we have one further constraint that all the classes, the variance covariance matrix are same. Okay, and by the similar technique we did as in the lecture 7, we can derive the decision function. So after some algebra, okay, we can find a decision function under the linear discriminant analysis is given by, suppose we have two class case 2. So QC minus QD is given by QC minus mu D. So the average between the two classes. Transpose variance covariance matrix, take the inverse and multiply x. Okay, so you can think this is the weight and this is the x minus mu c transpose sigma inverse mu c minus mu d transpose sigma inverse mu d over 2 plus prior information pi c plus minus h log pi d. Okay, so the last two part is a constant alpha. So our decision function is again the linear format, so which is w times x plus alpha. Okay, linear. That's why this method is called linear discriminant analysis. And then we can see the example. So, for example, for the same data set as we introduced here, these two examples will fit different model with same data set. But now you see with the restriction that every class they share the same variance covariance matrix. In other words, the correlation between the two features x1, x2, they are same, and the locations are different. This is the mu c, this is the mu d. Okay, locations could be different, but the shape, variance covariance matrix is the same. and therefore we can also see these two counterplot shares so this is a decision boundary. Okay, and based on this, we can also derive the decision function QC minus QD, because this is a linear function, so we can have the contour plot is just the straight lines. And we set this equal to 0, we can also find the decision function. We can find decision function. And after you apply the logistic function, we can find the probability equal to 0.5 is this line. Okay, this line. So now for any point, if a point falls to here, we can say, oh, this point will be classified as a class C with the probability. If it's here, maybe with the probability 0.2. Okay, so with 20% chance, this X falls into this class C. Okay, so this also gives us the posterior probability is equals to the logistic transformations of this omega dot product with X plus alpha. Okay. So now for the multi-class problem. Okay. We just choose pick the class that maximize linear discriminant So for example, so we just want to find the term with the QC part. QC will be everything is here, and this part is here, is here. Okay, so to summarize, we have the QC X equals to mu C transpose sigma inverse X minus mu C transpose sigma inverse mu C over 2 plus log of the prior information pi C. Okay, and then we can apply this. We can get the linear classifiers for the different 10 digits for 10 digits. And the advantage of linear classifier to find the decision boundary we just need to solve the linear system. Linear system. For example, here we have the, because omega dot product with x plus alpha, you set this equal to 0, you solve for x. You solve for x. Okay, you can easily solve the decision boundary. This plot shows the classification. This is LDA, linear discriminant analysis for classifying digits. 0, 1, 9. Okay, so in the last few videos, we talk about the general discriminant analysis under the general normal distribution setting. And in next video, I'm gonna give you a little bit of summary of the classification methods we learned so far. And in next few classes, we're gonna move on to another topic: regression, logistic regression,